Deep in your chest sits a single bone that acts as a literal, legal timekeeper. Until it completely fuses, forensic scientists can prove exactly whether you're a minor or a legal adult.
Welcome to This Explainer. Today, we're exploring the seriously fascinating science behind chronological indicators in human long bone development. You can really think of the human skeleton as this highly intricate, decelerating biological clock. When we're first forming, this clock is ticking incredibly fast, with absolute pinpoint precision. But as we age, the gears kind of start to slow down. The ticking stretches out, and eventually, the whole thing basically grinds to a halt. How forensic anthropologists actually read this decelerating clock is, well, it's nothing short of incredible.
Okay, let's dive into this. There's a really fundamental distinction here that forms the absolute bedrock of this entire science. Think about it. Your birth certificate tells one story, right? That's your chronological age, which is simply the years, months, and days you've been alive since birth. But your bones, they tell a completely different story. That's your biological age, or the actual physical condition of your skeletal system. Forensic anthropologists are essentially trying to bridge the gap between these two numbers. They're looking at the biological evidence left behind to accurately predict the chronological truth.
Let's start with Section 1, fetal measurements, where the clock is ticking in weeks.
We're starting at the absolute beginning of the skeletal timeline. At this stage, biological changes are happening so rapidly that we can estimate age down to the precise week. 6 to 8. That's the exact number of weeks into intrauterine life when the primary ossification centers for your major long bones first show up. We're talking about the shafts of the humerus in your arm, the radius, the ulna, the femur, the tibia. The very foundation of your entire physical frame begins to solidify at this incredibly early, pinpointed moment.
And this brilliantly illustrates how experts use simple diaphyseal length measurements, which basically just means measuring the shafts of these tiny long bones. Forensic scientists actually use mathematical shortcuts called Haase's and Morrison's rules. It's wild how simple it is. For the first 5 months, a fetus's age in months is roughly the square root of its body length in centimeters. After 5 months, you just take the length in centimeters and divide it by 5. It's a remarkably straightforward calculation that reveals a highly precise gestational age. Now, beyond just simple measurements, specific markers act as definitive biological alarm clocks. The appearance of secondary growth centers in the knee, specifically we're looking at the distal femur and the proximal tibia, are absolutely critical markers here. If a forensic anthropologist spots these secondary centers, they know for a fact that they're looking at the remains of a full-term fetus. The biological clock strikes 0, right at the exact moment of birth.
Moving right along to Section 2, the juvenile fusion sequence, where the clock starts ticking in years. Once childhood kicks in, that super precise fetal growth slows way down. We aren't tracking time in weeks anymore. We're tracking it by watching the skeletal growth plates, known as epiphyses, as they slowly fuse together. Experts literally score these plates by checking, are they open, uniting, or completely fused? And the fascinating part is that this union follows a highly predictable sequential path. Step 1, fusion begins down at the elbow. Then, Step 2, it moves to the hip, ankle, and knee. Following that, Step 3, the wrist completes its fusion. And finally, Step 4, the whole sequence works its way all the way up the arm to the shoulder, ending with the clavicle.
Which brings us right back to our cold open. The medial, or sternal end of the clavicle, is literally the absolute last epiphysis in the human body to fuse. This usually happens somewhere between 17 and 30 years old, and because of that, your collarbone is the ultimate legal marker. In a forensic setting, the state of that clavicle is often the definitive biological evidence they use to prove whether someone has crossed those major legal thresholds of being 18 or 21 years old.
Now, a really crucial point you need to understand is that this timeline isn't identical for everyone. 2. That's the number of years, roughly, that female skeletons mature faster than male skeletons. Females generally hit these epiphyseal union milestones 2 full years earlier than males. It's a stark sex difference, and honestly, it's absolutely essential to factor that into every single forensic age estimation to make sure the data is accurate.
And hey, while we're on the topic of accuracy during childhood, let's briefly contrast long bone growth with dental development. Yes, diaphyseal lengths are still used through childhood, but a kid's linear bone growth becomes highly variable as they age. It's incredibly sensitive to genetics and environmental factors. It kind of bounces all over the place. Because of that crazy variability, forensic anthropologists often actually consider dental development to be a much more stable, reliable indicator of chronological age in kids.
All right, Section 3, reading adult bones. The clock basically grinds to a halt.
So by the time someone hits about 25, all of those predictable epiphyses have totally fused.
The easy-to-read milestones? Gone. Growth is completely finished. Since the growth plates are closed tight, forensic experts face a much harder job. They now have to look for wear and tear. Essentially, they're searching for microscopic scratches on the gears of our biological clock. They have to rely on assessing radiographic density, basically looking at the proximal ends of the humerus and femur for degenerative changes. Things like the thinning of the compact cortical bone or the expansion of the spongy bone inside. They're also looking at histomorphometry and broader degenerative conditions.
Now, what's really interesting about this is a technique called histomorphometry. This involves looking at cortical bone under a microscope to count what are known as secondary osteons. Basically, these are microscopic fragments produced during the constant lifelong process of bone remodeling. Think of it like this. As you age, your bone becomes more densely packed with these remodeled units. By counting them, scientists can estimate age with a standard error ranging from about 2.6 to 15 years. It is widely considered to be one of the absolute most accurate methods for aging adult remains.
Stepping back to a macro level, experts are also hunting for degenerative conditions on the joints and spine. The presence of osteophytes, which are these gritty, degenerative, bony outgrowths you'll see on the vertebrae or joint surfaces, acts as a really clear biological milestone. If you see those, it's a huge indicator that the individual is generally over 40 years of age.
Finally, let's look at Section 4. What skews the clock? The variables in the timeline.
Up to this point, we've been outlining a pretty standard biological progression. But of course, human bodies don't just exist in a vacuum, right? Forensic anthropologists constantly have to account for three massive variables that can completely distort natural timekeeping. First up is environmental stress. Second, we have secular trends, meaning global modern trends toward increased overall stature and much earlier maturation. This basically means that standards from 50 years ago might not accurately reflect modern populations at all. And third, population specificity. Rates of bone growth and fusion vary significantly by ancestry and geographical distribution. So to get the absolute highest accuracy, scientists literally have to use highly specific population standards.
To understand just how powerful these variables actually are, just look at the impact of environmental stress. Long bone development is incredibly sensitive to hardship. Extreme malnutrition and severe disease can literally hit pause on your biological clock's timeline. We're talking about delaying skeletal maturation by a massive 2 to 3 years, compared to a perfectly healthy individual.
So the big takeaway here is that our skeletons are incredible, but ultimately imperfect recorders of our lived time. We start with absolute pinpoint precision in the womb, ticking away in weeks. We track our youth through this amazingly predictable sequence of fusing joints. And then we endure adulthood, leaving microscopic scratches of wear and tear on our bones. But I want to leave you with this. If malnutrition, genetics, and modern life can alter your skeleton's timeline, what time is your biological clock really telling right now? It's a fascinating thing to ponder. Thanks for hanging out with us for this explainer, and definitely keep questioning the hidden science inside yourself.